In this video, we're going to be talking about the phenomenon known as blackbody radiation. But before we do, I forgot one thing in my previous discussion of light. And that is when we talk about frequency, we talked about cycles per second. Basically, how quickly is the light sort of moving through the wavelength, the waves are moving through a particular point. This again is the Greek letter nu that we represent this by. The unit for this is known as hertz. And just it means hertz literally means cycles per second, so it would also be represented by seconds to the -1, or 1 over seconds, or any of these are equivalent. So just one note on units. Wavelengths are always in units of distance, so like nanometers or meters or whatever, but frequencies are always in terms of cycles per second. And then when you multiply them together, you get meters per second, which is what you should get for a speed, for the speed of light. Okay, I wanted to make sure to mention that before we moved on. So in this video, we're talking about the phenomenon of blackbody radiation. So blackbody radiation is the light that comes off of things just because they're warm. So I have here a picture of a electric stove. Some of you may have this at home. Hopefully you don't, because they're kind of annoying to cook on. I used to have this both growing up and in my old house before I moved. These take a long time to warm up, so they're kind of annoying. But they are really good at demonstrating the idea of blackbody radiation. And so the idea is if you heat something up to a temperature, which you are doing with this electric coil on the stove if you're trying to cook, you can see it glow, right? And this glow is what we know as blackbody radiation. Now, there's a technical definition of what a blackbody is specifically, but for our purposes, it just means something that's warm and that emits light. And so this is one example. We are blackbody. We are basically blackbody radiation emitters as well. It's just you can't see us glow because most of our light that we emit is not visible light, but instead in the infrared. And so we actually use this fact so we emit infrared light. And you can use this fact to make night vision goggles, or so you can see things in the dark. So if you have a camera that can see in the infrared, you can see people even when the lights are off because we glow. So that's just kind of a fun fact. Now, why is this relevant to talking about atoms? Well, back in the early 1900s and late 1800s, scientists were measuring the properties of blackbody radiation. And so if you're familiar with a stove or a flame or something, as it gets hotter, as temperature increases, the peak wavelength decreases. What does that mean? It means the color of the light changes as the blackbody you're considering gets hotter and hotter. So that's, for example, why we emit infrared light, because we're not as hot as the stove. We don't want to be that hot. We're around 98.6 degrees, right? And that's our temperature on our skin's a little bit lower than that in terms of Fahrenheit, or 37 roughly Celsius. But if we plot this, I'm going to draw a crude sketch here. If we plot blackbody radiation, what we're often looking at is the amount of light on the y-axis here and the wavelength on the x-axis here. So we can plot this for different temperatures, and we'll have like basically UV here, draw a little bit here for visible light here, and then we'll get infrared light here. And this is what scientists measured this for black bodies at different temperatures. And so what's experimentally observed is you get something that looks like this, roughly speaking. This would be maybe 6,000 Kelvin or something, quite warm. This is like the temperature of the sun, sort of warm. Or if you're looking at something more like this stove here, you'll get something more like this. Or if you're looking at a person, we'll peak further out here. But so this would be like 300 Kelvin, whereas this is maybe like 450 Kelvin or something like that. But the main idea being that this peak is shifting to the left. So as things get hotter, they will, number one, they'll get brighter. I didn't represent that very well here, but they get brighter, and the peak of the wavelength shifts to smaller wavelengths, more energetic photons. So our stove here, if we were able to keep heating this stove, it starts as sort of red. That's on the very edge of the visible spectrum. And as we heat it more and more, it'll turn more and more white as we get more colors mixing in as this shifts. And that's why the sun produces a nice white light. We think of it as being yellow, but it's really white because it's a very, very hot object that emits blackbody radiation. So how is this relevant to what scientists were observing? So they observed this property and they said, well, let's try and model this with what we understand about physics. And according to the models, I'm going to draw the model in red, what we should get is sort of something, it agrees pretty well here, but then just keeps going up. And according to the models that were made with classical physics like Newton came up with back in the 1700s or earlier 1800s, they couldn't explain what was actually observed. So red here is like, this is the incorrect theoretical view, and the white lines are the experimental data. So scientists were really puzzled by this, and they actually, this whole disagreement between the theoretical and visible, theoretical and experimental data was termed the ultraviolet catastrophe, because there's really just couldn't explain what the heck was going on here. Catastrophe. Got to think about that spelling. So, ultraviolet catastrophe, scientists didn't understand what was going on. Well, this puzzled a lot of scientists, and there was a lot of work that went into this. And one scientist, Max Planck, came up with a way to get the model to work out. He said, okay, well, if we imagine that the energy inside of our blackbody comes in discrete chunks, and he used this based on the frequency. So the energy comes in, I need an n here. So where n here is equal to some integers, so it's like 1 or 2 or 3, it's like specific numbers, and it depends on the frequency of the light. But the energy can only come in specific small amounts. And he called this a quantum of energy. Quantum just meaning a specific amount. So if we think about it this way, if we have sort of a ladder representing our energy, each rung on the ladder is 1 h nu tall. And you can't ever have anything in between those rungs of the ladder, which is very counterintuitive. This is not how we usually think about energy. We usually think you can put in a little bit or a little bit more. You can sort of do however much energy you want. But Planck's theory, Planck's way to make this work for blackbody radiation was say energy only comes in specific amounts, and we can figure out how much that is. He worked it out, and he got an agreement with between the experimental and his theoretical result, and that allowed him to calculate the value of this constant, which we call Planck's constant in his honor. And it's a very small number, but it is finite, right? There is a distinct amount of energy. And so that resolved the ultraviolet catastrophe, but then the question was like, why? Why does energy only come in small chunks? So we're going to talk about one more experiment that scientists were looking at in the late 1800s, early 1900s that also showed this same effect of seeing energy come in distinct chunks. Also involves light.